Ancient Indian and Greek philosophers have always wondered about the unknown and unseen form of matter. The idea of divisibility of matter was considered long back in India, around 500 BC. An Indian philosopher Maharishi Karnad postulated that if we go on dividing matter, Padarth, we shall get smaller and smaller particles. Ultimately, a time will come when we shall come across the smallest particles beyond which further division will not be possible. He named these particles Parmanu. Another Indian philosopher, Pakada Katayama, elaborated this doctrine and said that these particles normally exist in a combined form which gives us various forms of matter. Around the same era, ancient Greek philosophers, Democritus and Leucippus suggested that if we go on dividing matter, a stage will come when particles obtained cannot be divided further. Democritus called these indivisible particles atoms, meaning indivisible. All this was based on philosophical considerations and not much experimental work to validate these ideas could be done till the 18th century. By the end of the 18th century, scientists recognized the difference between elements and compounds and naturally became interested in finding out how and why elements combine and what happens when they combine. Antoine Lavoisier laid the foundation of chemical sciences by establishing two important laws of chemical combination. 3.1 Laws of chemical combination. The following two laws of chemical combination were established after much experimentation by Lavoisier and Joseph L. Proust. 3.1.1 Law of conservation of mass. Is there a change in mass when a chemical reaction, takes place? Which can be explained by activity. 3.1, which is discussed in activity section. Law of conservation of mass states that mass can neither be created nor destroyed in a chemical reaction. 3.1 Laws of chemical combination. The following two laws of chemical combination were established after much experimentation by Lavoisier and Joseph L. Proust. 3.1.1 Law of conservation of mass. Is there a change in mass when a chemical reaction, takes place? Which can be explained by activity. 3.1, which is discussed in activity section. Law of conservation of mass states that mass can neither be created nor destroyed in a chemical reaction. 3.1.2 Law of constant proportions. Lavoisier, along with other scientists, noted that many compounds were composed of two or more elements and each such compound had the same elements in the same proportions, irrespective of where the compound came from or who prepared it. In a compound such as water, the ratio of the mass of hydrogen to the mass of oxygen is always 1:8, whatever the source of water. Thus, if 9 grams of water is decomposed, 1 gram of hydrogen and 8 grams of oxygen are always obtained. Similarly in ammonia, nitrogen and hydrogen are always present in the ratio 14:3 by mass, whatever the method or the source from which it is obtained. This led to the law of constant proportions, which is also known as the law of definite proportions. This law was stated by Proust as in a chemical substance the elements are always present in definite proportions by mass. The next problem faced by scientists was to give appropriate explanations of these laws. British chemist John Dalton provided the basic theory about the nature of matter. Dalton picked up the idea of divisibility of matter, which was till then just a philosophy. He took the name atoms as given by the Greeks and said that the smallest particles of matter are atoms. His theory was based on the laws of chemical combination. Dalton's atomic theory provided an explanation for the law of conservation of mass and the law of definite proportions. About John Dalton. John Dalton was born in a poor weaver's family in 1766 in England. He began his career as a teacher at the age of 12. 7 years later he became a school principal. In 1793, Dalton left for Manchester to teach mathematics, physics and chemistry in a college. He spent most of his life there teaching and researching. In 1808, he presented his atomic theory, which was a turning point in the study of matter. Dalton's atomic theory. According to Dalton's atomic theory, all matter, whether an element, a compound or a mixture, is composed of small particles called atoms. The postulates of this theory may be stated as follows: Point 1, all matter is made of very tiny particles called atoms. Point 2, atoms are indivisible particles, which cannot be created or destroyed in a chemical reaction. Point 3, Atoms of a given element are identical in mass and chemical properties. Point 4. Atoms of different elements have different masses and chemical properties. Point 5. Atoms combine in the ratio of small whole numbers to form compounds. Point 6. The relative number and kinds of atoms are constant in a given compound. 3.2 What is an atom? Have you ever observed a mason building walls, from these walls a room and then a collection of rooms to form a building? What is the building block of the huge building? What about the building block of an anthill? It is a small grain of sand. Similarly, the building blocks of all matter are atoms. How big are atoms? Atoms are very small. They are smaller than anything that we can imagine or compare with. More than millions of atoms when stacked would make a layer barely as thick as this sheet of paper. Look at the table and study the size of atoms and comparison with other objects. We might think that if atoms are so insignificant in size, why should we care about them? This is because our entire world is made up of atoms. We may not be able to see them, but they are there, and constantly affecting whatever we do. Through modern techniques, we can now produce magnified images of surfaces of elements showing atoms. 3.2.1 What are the modern-day symbols of atoms of different elements? Dalton was the first scientist to use the symbols for elements in a very specific sense. When he used a symbol for an element, he also meant a definite quantity of that element, that is, one atom of that element. Berzelius suggested that the symbols of elements be made from one or two letters of the name of the element. In the beginning, the names of elements were derived from the name of the place where they were found for the first time. For example, the name copper was taken from Cyprus. Some names were taken from specific colors. For example, gold was taken from the English word meaning yellow. Nowadays, IUPAC, International Union of Pure and Applied Chemistry, approves names of elements. Many of the symbols are the first one or two letters of the element's name in English. The first letter of a symbol is always written as a capital letter, uppercase, and the second letter as a small letter, lowercase. For example, 1, hydrogen, capital H, 2, aluminium, A, small l and not A, capital L, 3, cobalt, C, small o and, not, C, capital O. Symbols of some elements are formed from the first letter of the name and a letter, appearing later in the name. Examples are, 1, chlorine, Cl, 2, zinc, Zn etc. Other symbols have been taken from the names of elements in Latin, German or Greek. For example, the symbol of iron is Fe from its Latin name ferrum, sodium is Na from natrium, potassium is K from gallium. Therefore, each element has a name and a unique chemical symbol. The above table is given for you to refer to whenever you study about elements. Do not bother to memorize all in one go. With the passage of time and repeated usage, you will automatically be able to reproduce the symbols. Aluminium, A, L, copper, C, U, nitrogen, N, argon, A, R, fluorine, F, oxygen, O, barium, B, A, gold, A, U, potassium, K, boron, B, hydrogen, H, silicon, S, I, bromine, B, R, iodine, I, silver, A, G, calcium, C, A, iron, F, E, sodium, N, A, carbon, C, lead, P, B, sulfur, S, chlorine, C, L, magnesium, M, G, uranium, U, cobalt, C, O, neon, N, E, zinc, Z, N. Look at the table and try to practice twice a week. This will help you to remember the name and symbols of elements.